Hello and welcome to my presentation. It is my pleasure to present HPOBench at this NeurIPS 2021 Datasets and Benchmark track. Our library for multi-fidelity optimization benchmarks has been developed by a great team from the universities of Freiburg and Hanover. And it's publicly available, so please feel free to use and extend it. So what is this library for and why should you care? The amount of available data is growing and machine learning is applied everywhere. The size and complexity of these models is larger than ever. But still we want to perform hyperparameter optimization. And multi-fidelity optimization can efficiently optimize such expensive hyperparameter optimization problems. It makes use of cheaper approximations such as the number of epochs, iterations or dataset size. And it has been shown to provide tremendous speed-ups. But currently there is no standardized set of benchmark problems, which would be crucial to develop, improve and compare methods. While there are a few benchmarks, our community really lacks a set of realistic, diverse and computationally cheap standardized benchmarks. And thus we propose HPOBench, a collection of reproducible benchmarks available under one API. Concretely, our contributions are: we do have the first set of more than 100 containerized multi-fidelity HPO problems. We have the first set of benchmarks that are available as both raw and tabular versions and support multi-objective and transfer HPO. And to validate the usefulness of our benchmarks, we conducted an exemplary large-scale study with more than 10 optimization methods. So before I dive deeper into our benchmarks, let me summarize what we consider a benchmark. A benchmark consists of a parameterized algorithm, for example neural network, some data it can be trained on and a loss function to evaluate the performance of this algorithm. The bounds for all hyperparameters are defined by a configuration space and lower fidelities are defined by a fidelity space. Now the optimizer can query the benchmark with a configuration and observe a function value and cost. Additionally, there are three features that we believe a good collection of benchmarks should have. First of all, they should be efficient, so there should be a way to obtain meaningful results with few computational resources. Second, they should be reproducible, and with that we mean that the benchmark should not only run once, but also in 1 month or even 10 years. And third, they should be diverse and cover various problems with different characteristics. So first, efficiency. I just explained the concept of a raw benchmark, which actually trains an algorithm for each query. While this is the most realistic benchmark, it is also the most expensive one. For this, we also do have tabular benchmarks returning a table lookup and surrogate benchmarks returning the prediction of a machine learning model. Both types are widely used by the community because they require less computational resources and still yield realistic benchmark problems. The second feature was reproducibility. Reusing benchmarks can be complicated. While building the library, we observed that conflicting, outdated or updated versions can either change the benchmark or require a time-consuming and careful setup. To avoid that, for every benchmark we did the following 3 steps. First, we collect all components and made them available under a unified interface. Second, we collected all dependencies and fixed the versions. And 3, we packaged everything in a singularity container. And with that we can ensure that the benchmark can be run again using the same environment now and in the future, without ever installing dependencies again. This also makes the library low maintenance for us. The third point was flexibility. Our initial collection comprises a diverse set of existing community benchmarks from various domains such as reinforcement learning, NAV, and joint NAS and HPO. They all have been used before and they do have small continuous spaces but also mixed high-dimensional spaces. Also, we do have raw, tabular and surrogate benchmarks. And additionally, we created a new large set of 88 more benchmark problems, which consists of 5 machine learning algorithms, each evaluated on up to 20 datasets. Each of these benchmarks is available as both tabular and raw benchmarks. Finally, our empirical study. We conducted a large-scale study with more than 10 optimization methods and started 2 exemplary research questions. Do advanced methods improve over random baselines? And are multi-fidelity methods better than single-fidelity methods? On the right, you can see an example plot for a single benchmark. But in the paper, we have much more plots, results, and tables. The short answer to this question is yes. But for the longer answer, I recommend to read our paper or come talk to us at the poster. So let me conclude. We propose HPOBench, a collection of more than 100 multi-fidelity optimization problems. It is easy to install, easy to use, and easy to extend. You can use our benchmarks for a lot of interesting studies and to improve and develop new multi-fidelity methods, and I'm really looking forward to see that. That's already it for this short presentation. Thank you for listening. Please use our library, leave us a star on GitHub if you like it, and since it's open source, we welcome your contribution. Thank you.